Section 1. Introduction. In video 10 we discussed prime factorization in z adjoin root 2. The rational prime p either factorizes further or remains inert in z adjoin root 2 according to whether 2 is a square or not a square mod p. And for almost all values of p, if p factorizes, then it splits into two distinct factors. The only exception to this was when p equals 2. Here's a summary of the strategy we took. The norm function in z adjoin root 2 sends x plus y root 2 to x squared minus 2y squared. So the norm of p is p squared, and if p factorizes further non-trivially, say as alpha times beta, then alpha and beta both have norm plus or minus p, and conversely. In other words, we're looking for integers x and y, such that x squared minus 2y squared equals plus or minus p. Then we set alpha as x plus y root 2, and beta is plus or minus x minus y root 2, according to whichever sign you need. Now, using the fact that z adjoin root 2 was a UFD, we showed that this was equivalent to the existence of an integer z, such that z squared is 2 mod p. In other words, 2 is a square mod p. Is there anything special about 2 in this proof? Could we just replace all of these instances of 2 with some other integer n in this proof to get a similar result? Well, let's try it inside z adjoin root n. At one stage in our proof, we do need to assume that z adjoin root n is a unique factorization domain. And also, just to be pedantic, let's assume that root n isn't an integer already. Okay, under these assumptions, our proof works exactly as before. P factorizes in z adjoin root n if and only if n is a square mod p. So, we have an integer n, a prime number p, and we want to answer the question, when is n a square mod p? In other words, when is n over p equal to 1, where n over p in these square brackets is the Legendre symbol from the previous video. To calculate this, we'll start by reducing to a special case by factorizing n as a product of prime numbers, q1 times q2 and so on up to qk. They're all rational primes, except maybe one of them is minus 1 if n is negative. Now, the Legendre symbol is multiplicative, so we can write n over p as the product of q1 over p up to qk over p. Right. The upshot here is, if we have an easy way of calculating q over p for all primes q, and minus 1 over p, then we know how to calculate n over p for any integer n. Let's just quickly note some cases that we've already done. We calculated minus 1 over p in video 5. We just finished calculating 2 over p in video 11. And there are two uninteresting cases. The case when q equals p isn't very interesting because if n has a factor of p in it, then n is just 0 mod p. And the case when p equals 2 isn't interesting because everything mod 2 is either 0 or 1 and they're both squares. We still haven't addressed any of the other cases, in other words, the cases where p and q are distinct odd primes. But luckily we've now built up enough machinery to do this quite easily. Section 2. Quadratic reciprocity. We'll start off by taking q to be an odd prime. Now in video 11, we wrote a square root of minus 7 as a sum of roots of unity. It turned out to be 1 over 7 zeta to the 1 plus 2 over 7 zeta squared and so on up to 6 over 7 zeta to the 6, where zeta was some 7th root of unity. We're going to apply our trick from video 10, raising both sides to the power q plus 1 and then reducing mod q. Let's rewrite the left-hand side by taking out all the minus 1s and a single factor of 7, so that we're left with 7 to the power q minus 1 over 2. Okay, this part here is going to be plus 1 if q plus 1 over 2 is even, and minus 1 if q plus 1 over 2 is odd. Okay, let's bring this 7 down. And Euler's criterion tells us that mod q, this part is equal to the Legendre symbol 7 over q. Okay, let's raise the right-hand side to the power q plus 1. Well, we can immediately write it as this element to the power q times one more copy of the same element. And now mod q, we can apply the special form of the binomial theorem we saw in video 10 to this first factor to bring that power of q inside the bracket. And let's just bring down the second factor unchanged. And now if you tried the exercise in video 11, you might spot what to do next. We can multiply the top number of all of the Legendre symbols by q squared without altering their value. Then we can factorise out a q over 7 from the first bracket. Now, this sum here is just a rearrangement of this sum here, provided q isn't equal to 7. They have the same terms, just in a different order. So they're both equal to the same square root of minus 7 that we started with. So we can multiply them together to get minus 7. We'll tidy all this up in a minute, but for now let's just notice something about this equality. Ignoring all the minus 1s and 7s, we have something to do with 7 over q on the left-hand side, and something to do with q over 7 on the right-hand side. Why might this be useful? Well, let's take a large value for q, say 10,009. The Legendre symbol 7 over 10,009 asks whether 7 is a square mod 10,009. So we have to calculate 1 squared, 2 squared, 3 squared, 4 squared, and so on, mod 10,009, and see whether we spot a 7 anywhere. Right, this is really inefficient and it's really slow to calculate. But if we're able to flip the Legendre symbol and get something related, the problem becomes much easier. After all, in the symbol 10,009 over 7, the top number is being considered mod 7 now. Since 10,009 is just 6 mod 7, we could rewrite the symbol as 6 mod 7. Now all we need to do is calculate the squares mod 7, which is a much smaller task, especially if you're working by hand. We see whether we can spot 6, and we can't. 6 is not a square mod 7, so this symbol is equal to minus 1. Okay, so if we can understand this relation in the middle between the two Legendre symbols, we can make calculating Legendre symbols much easier. In the general case, we're going to want to replace all these 7s by some general odd prime p, which isn't equal to q. This is also going to have a knock-on effect on everything else. Of course, all these 7s will change, but importantly, as we saw last video, some of these signs will change too. So let's start again. Let p and q be distinct odd primes. Let zeta be a pth root of unity. Then we saw last video that one of the square roots of the Legendre symbol minus 1 over p times p is equal to the sum of I over p times zeta to the I, as I ranges from 1 to p minus 1. Now there's a plus or minus on the left. It doesn't actually matter which of the two square roots we have because we're about to raise both sides to an even power. In fact, let's raise both sides to the power q plus 1, which is even, and reduce modulo q as before. On the left we get minus 1 over p to the power of q plus 1 over 2, times 1 factor of p, times all the other factors of p, that's q minus 1 over 2 of them. And then by Euler's criterion, when we reduce mod q, that final factor is just equal to the symbol p over q. When we do the same thing on the right, we have q plus 1 copies of this sum multiplied together, which we can again write as q copies times 1 copy. Applying the binomial theorem mod q allows us to bring that power of q inside the bracket. We're allowed to multiply through by the Legendre symbol q squared over p because that's just equal to 1. And then we can factorise out a q over p. Okay, now finally these two expressions are both just the same terms added up in a different order, so they're both equal to our original square of minus 1 over p times p. So when we multiply them together, we get minus 1 over p times p mod q. So finally we have some sort of relationship between p over q and q over p as we wanted. Now let's tidy it up and see what we can learn from it. I'll let you check that when we rearrange this we get p over q times q over p equals minus 1 over p to the power q minus 1 over 2, everything taken mod q. But notice that the thing on the left hand side is equal to plus or minus 1, and the thing on the right hand side is equal to plus or minus 1. So if they're equal mod q, then they must be equal, because plus 1 and minus 1 are distinct mod q. Okay, so here's our relation, and you'll often see the right hand side written more symmetrically as minus 1 to the power p minus 1 over 2 times q minus 1 over 2. Personally, I think this still obscures the point. I much prefer to think about it as a formula for flipping the Legendre symbols, as follows: p over q equals q over p when either p or q is 1 mod 4, or both, and p over q is minus q over p when both p and q are 3 mod 4. This is called the law of quadratic reciprocity. By the way, remember that we're really interested in calculating n over q for arbitrary integers n, so as well as the law of quadratic reciprocity, which works for p and q distinct odd primes, for a full answer we need to remember from video 10 how to work out the value of the symbol 2 over q, this is often called the second supplement to quadratic reciprocity, and when working with negative values of n, we need to remember from video 5 how to calculate the value of minus 1 over q, this is often called the first supplement to quadratic reciprocity. So here's an exercise. Calculate the value of the Legendre symbol 167 over 199 using quadratic reciprocity. You should be able to use these rules above to reduce this problem to a much smaller one that you can calculate by hand without writing out all the squares mod 199. Okay. Once you've done that, using this fact, determine whether or not the rational prime 167 factorizes in z-adjoin root 199, which happens to be a unique factorization domain. Section 3. Non-unique factorization domains. The story is similar here, but a bit trickier, so I'll just state how it works in a specific example without any kind of justification, and I'll leave you with a reference to somewhere to read more. Let's look at z-adjoin root minus 5. I'll just start off by reminding you that the norm of an element a plus b root minus 5 is the product of its two embeddings into the complex plane, that's a plus b root minus 5 times a minus b root minus 5, which comes out to a squared plus 5b squared. Now, we know that this ring isn't a unique factorization domain. In fact, this was our motivating example for switching from prime numbers to prime ideals all the way back in videos 2 and 3. We saw that the number 6 could be factorized as 2 times 3, or as 1 plus root minus 5 times 1 minus root minus 5, and that all of these factors were irreducible inside this ring, so this factorization is non-unique. Then we conjectured from this that there should be some underlying prime ideals. So for example, 3 and 1 plus root minus 5 should share a smaller prime ideal factor. Since 3 has norm 9, and 1 plus root minus 5 has norm 6, we wanted their shared prime ideal to have norm 3, the greatest common divisor of 9 and 6. And it turned out that their ideal sum, 3, 1 plus root minus 5, was exactly what we were looking for. So this non-principal ideal must be one of the prime ideals dividing the ideal 3. The other one is given by swapping this plus sign for a minus sign, plus root minus 5 and minus root minus 5 corresponding to the two embeddings. So, can we use this template to factorize other prime numbers? For example, how does the number 7 behave in z-adjoin root minus 5? Well, the element 7 has norm 49, and if we can find another element of norm 7 times something, maybe their ideal sum will have norm 7. This would make it a prime ideal dividing the ideal 7. Here's how we're going to find that element. As a helpful tool, let's write down the minimal polynomial satisfied by this number root minus 5. It's more usual to pick x squared plus 5, but actually it's going to be convenient for me in this video to take the negative of that, so I'll write that as minus 5 minus x squared. Now let's try to factorize this mod 7. Minus 5 minus x squared is the same as 9 minus x squared mod 7. I've just added 14. And so it factorizes as a difference of two squares. It's 3 plus x times 3 minus x mod 7. Now I'm going to substitute x equals root minus 5 into this expression, and then I'm going to forget about the polynomial entirely. Before I do that though, I want to highlight one thing. When we set x equals root minus 5 in here, the left-hand side is 0. That's how we chose this polynomial in the first place. Okay? That ensures that 3 plus root minus 5 times 3 minus root minus 5 should be 0 mod 7. Well, in fact, if we multiply out the brackets directly, we can see that it's equal to 14. Notice that this product here that we found is just the norm of the element 3 plus root minus 5. Compare it to the formula. So this is what's going to play the role of our mystery element above. Let's just substitute that in. We found an element, 3 plus root minus 5, of norm 14, and we can check that the ideal sum, 7, 3 plus root minus 5 does in fact have norm 7. This is one of the primes dividing the ideal 7. I won't prove it here, but this is what happens more broadly too. If minus 5 minus x squared factorizes mod p, then p factorizes further as a product of two prime ideals in z adjoin root minus 5, so it splits or ramifies. If that polynomial doesn't factorize, then neither does the ideal. In other words, the ideal p remains inert. Okay, how is this related to what we did earlier? Well, when you're attempting to factorize minus 5 minus x squared, modulo some prime p, you'll quickly notice that it's going to have to factorize as a plus x times a minus x for some integer a where a squared is minus 5 mod p. This means that minus 5 is a square mod p. In other words, the Legendre symbol minus 5 over p is equal to 1. Okay, we can say more about this too. Though at this stage, I'm first going to exclude the cases when p equals 2 or 5. This Legendre symbol is only defined when p is odd, and when p is co-prime to the top argument, so I'll exclude 2 and 5. Now let's use what we just learned about quadratic reciprocity to see whether we can calculate this. Firstly, the symbol on the left is just equal to minus 1 over p times 5 over p. The first supplement to quadratic reciprocity tells us how to calculate minus 1 over p. It's just 1 if p is 1 mod 4 and minus 1 if p is 3 mod 4. And the main result of quadratic reciprocity tells us that 5 over p is just equal to p over 5. Let's list out the squares mod 5. Okay, so the symbol p over 5 is 1 if p is 1 or 4 mod 5, and it's minus 1 if p is 2 or 3 mod 5. Notice that I've already ignored the case p equals 0 mod 5 because that never happens. Okay, let me just neaten this up. P factorizes in z adjoin root minus 5 when this polynomial factorizes mod p, which happens if and only if this product is 1. And we can calculate both of the factors in the product using congruences mod 4 and mod 5. We should be able to read off a full answer from here. Okay, let's combine these separate conditions, mod 4 and mod 5, into one condition, mod 20. Now there's a tool called the Chinese remainder theorem for this, but in this small case it's not too laborious to just write the cases out by hand. So here are all the numbers mod 20. Here's how they reduce mod 4 and mod 5. Now looking first at the value of minus 1 over p, we're only interested in the cases when p is 1 or 3 mod 4. So if p is 0 or 2 mod 4, we don't need to calculate anything. We're not interested in these columns of the table. And that makes sense because that would make p even, and we've already excluded that case. So let's just get rid of all of those columns. Now let's fill in the value of the symbol minus 1 over p in this row, according to the value of p mod 4. It's a plus 1 if p is 1 mod 4, and a minus 1 if p is 3 mod 4. Okay, let's do the same for 5 over p. We're only interested in the cases when p is 1, 2, 3, or 4 mod 5, so not 0 mod 5. Let's get rid of those columns. And the value of 5 over p is plus 1 if p is 1 or 4 mod 5, and minus 1 if p is 2 or 3 mod 5. So now we can multiply these signs together in columns to find minus 1 over p times 5 over p. Okay, here's where it equals plus 1, that's when p factorizes further, and here's where it equals minus 1, which is when p doesn't factorize further. So if p is 1, 3, 7, or 9 mod 20, then it factorizes further, and if p is 11, 13, 17, or 19 mod 20, then it doesn't. You might remember that this is the pattern I mentioned without proof in video 3. In fact, if p is 1, 3, 7, or 9 mod 20, then p splits. If it's 11, 13, 17, or 19 mod 20, then it's inert. And if it's either of these two primes I excluded at the top, it ramifies. Section 4. Another type of quadratic ring. There are actually two types of quadratic rings of interest to us. We've mostly talked about rings of the form z adjoin root d, but there is a second type. I'll say a little bit more about why in a bonus video coming up shortly. For now, let me just remind you that we've actually seen a few of these. We've occasionally dealt with z omega, for example, where omega is a cube root of unity. Let me draw its lattice picture, and here's omega. Just to make the pattern that'll emerge a little clearer, I'm going to rewrite this ring as z adjoin 1 plus root minus 3 over 2. So I've chosen this generator of the lattice rather than omega. Some other rings we've seen include z adjoin 1 plus root minus 7 all over 2 in video 5, and z adjoin 1 plus root 13 over 2 in video 6. We've also seen that all three of these rings are unique factorization domains, though there are non-UFD examples of this type too, such as z adjoin 1 plus root minus 23 over 2, or z adjoin 1 plus root 229 over 2. Let's just take one of the UFDs, say z adjoin 1 plus root 13 over 2. The other UFDs are going to work similarly. Alright, as in video 6 and beyond, I want to try and make sure that I'm not biased towards any particular embedding of this ring into the complex plane. So for a second, let me just denote this element by alpha. If I square alpha, I get 7 plus root 13 over 2, so we can see that alpha squared is actually just alpha plus 3. Okay, so we can rewrite this ring without reference to any particular numbers outside of z, such as square roots of 13, by writing it as z adjoin alpha, where alpha satisfies the polynomial alpha squared minus alpha minus 3. The benefit of rewriting it like this is that if we forget where alpha came from originally and just take this equation to be our definition of alpha, then alpha could be either 1 plus root 13 over 2 or 1 minus root 13 over 2. And these are our two embeddings of this ring into the complex plane. This now allows us to calculate our norm function. The norm of x plus y times alpha is the product of its two embeddings. And if I expand this out, I get x squared plus xy minus 3y squared. Great, so now we can try to proceed as before. When does a rational prime p factorize further in z adjoin alpha? Well, exactly when some element has norm plus or minus p. That is, when there exist some integers x and y, such that x squared plus xy minus 3y squared equals plus or minus p. So we want to solve this equation. Let's go back to what we did in video 10, where we had z adjoin root 2. There, the norm function sent x plus y root 2 to x squared minus 2y squared, and we wanted to solve the equation x squared minus 2y squared equals plus or minus p for prime numbers p. I'll put that up here on the right for us to compare. And in fact, just to keep things simple so that we're not carrying extra signs around, I'm just going to deal with the case plus p, so I'll erase this plus or minus sign on the left too. Now, by reducing mod p, rearranging, and then dividing by y squared mod p, we saw that this could only happen when there existed some integer z whose square was 2 mod p. Okay, can we get a similar necessary condition on the left? The trick is going to be to adjust this equation so that the left-hand side is a square in z. Okay? X squared plus xy minus 3y squared isn't a square at the moment, and it's hard to make it one because of that xy term in the middle. But if you were playing around with this, you might think to multiply both sides by 4. We get 4x squared plus 4xy minus 12y squared on the left, and the reason this is useful is because 4x squared plus 4xy plus y squared is a square. So if I rewrite minus 12y squared as y squared minus 13y squared, then these first three terms form a square, 2x plus y all squared. Okay, so again, reducing mod p, rearranging, dividing by y squared, we see that this can only happen when there exists some integer z whose square is 13 mod p. We've reduced this to a case that we've already solved. Here are a few exercises for you. Firstly, just like back in video 10, we've only proved the rightwards implication here. Show that this is actually an if and only if statement. Use the proof we gave for z adjoin root 2 back in video 10, and it'll also be helpful to use the fact that both square roots of 13 are in z adjoin alpha, and that z adjoin alpha is a UFD. Secondly, what happens when the right-hand side is minus p? Thirdly, by using quadratic reciprocity like we did earlier, work out which primes factorize in this ring. Your answer should look something like an odd prime p factorizes further in z adjoin 1 plus root 13 over 2, if and only if p equals something mod something. Try to fill in these blanks. Here's another exercise of a different kind. See how much you can say about prime factorisation inside z adjoin 1 plus root 257 over 2, noting that this ring is not a UFD. Try combining the approaches of the previous two sections. Section 5. Where to go from here? Hopefully over the course of these videos, I've managed to convince you that these lines of inquiry can lead to interesting places. One thing you might want to do at this stage is see a formal exposition of this material, so I'm going to take this opportunity to give a few references. There are plenty of great books on algebraic number theory out there that tackle similar content. One example is Marcus's Number Fields, which I highly recommend, but there are many others. But if you're not used to reading very formal mathematics, any textbook like this is likely to be quite difficult. For that reason, I have to recommend Keith Conrad's excellent set of notes online that treat many of the topics we've covered in these videos in detail, rigorously, purely for the case of quadratic extensions of Z. I'll leave a link to that and a few other references I like in the video description. However, at this stage, you may have more questions than answers, especially if you've seen other number theory courses in the past. And so from this point on, I plan to make a few shorter, probably more informal videos, some of them tying up various threads that I've left hanging, such as gaps I left in the exposition or questions that have still remained unanswered, and some of them introducing you to a few of the many more complex and interesting topics that can follow on from here.